So this topic is going to be about electronic excited states and what happens to energy as you absorb inside of a molecule. So we're going to take the example of diatomic molecules, which have a curve is typically like this. So as a function of distance, you have the electronic energy and this distance right here is called the equilibrium bond distance. On top of the electronic energy is the vibrational energy, and the lowest vibrational energy has a quantum number V equals 0, and so this is what it would look like for a diatomic. Higher excited vibrational levels would be like V equals 1 and 2 and so on. All right, so what we're going to do is actually talk about the excited state. So every electronic state of a molecule, there'll be a ground state, but then there will be an excited state as well. So we're going to draw an excited state, more or less with the same overall shape. It will not be identical, but in this case, we're going to make it pretty close. And so this will have a V equals 0 as well. It'll have its own little RE, so we'll call it prime. And it's very common in electronic spectroscopy to denote the originating or the ground state, the level by a double prime, and the excited state by a single prime. So we're going to label these with prime and double prime. And if the curves are more or less on top of each other, then RE is about the same as RE. RE double prime is about the same as RE prime. And then, of course, there's a similar set of frequencies here as well. Okay, so this energy difference is the vibration of the ground state for the molecule. For the electronically excited state, this energy difference will not necessarily be the same vibrational frequency because the bond will be a different strength, and that'll mean the frequency will be a different frequency. Okay, so there are several excited states that look like this. Some of them may not even have a dip. They may just go straight from high energy to low. Those will be states that aren't bound, but this fall apart. And of course, the last thing to remember is that the depth of the well is basically related to the bond energy. So strong bonds will have a deep well, weak bonds not so deep. Okay, so now we're going to look at transitions from the ground state to the excited state. So the easiest thing to do is assume, first of all, that the molecules are in the ground vibrational state at room temperature. That's a pretty good approximation. And as the bond vibrates in this diatomic molecule, the distance will get longer and shorter, back and forth, back and forth. So it can excite at various, when the bond is at various distances. And so the distribution of the distances looks like a Gaussian curve, at least for V equals 0. And so that means sometimes when the bond is short, you'll excite. When the bond is long, you'll excite, and so on. But the most common excitation is going to go straight up. This is called a vertical excitation. Okay? And the reason it's called vertical is because you're not going from one distance to another distance, because when the light hits the molecule, it's absorbed instantaneously. The molecule doesn't even have time to change the bond distance before it suddenly finds itself in this new electronic state. Okay, now by selection rules, generally you'll only see this absorption if the multiplicity of this state is the same as that state. The labels for these states, if this is the ground state of the molecule, this gets a capital X. And then the first excited state will be a capital A, and then the second excited state would be capital B, and so on through the alphabet. If the excited states don't have the same multiplicity as the ground state, they get labeled with a lowercase a, lowercase b, and so on. But the first transitions we're going to look at are going to be the ones that are allowed by spin symmetry. That's to say the spin does not change. Okay, so that's that excitation, but you can also go to V equals 1 just as easily in the excited state as from 0 to 0. And so the first transition, you might label it 0 to 0. And the second transition, you might label it 0 to 1. So the first number is the vibration quantum number in the ground state, and then the second number will be the vibration quantum number in the excited state. So what you'll see is a series of peaks like this. And so now I'm going to draw the spectrum, what you would observe in a experiment. Okay, so you would look at the frequency of the photon, where the frequency of the photon, when you multiply by h, is equal to the energy difference between this energy level and this energy level. So what you'd see is whatever transition here, the 0, 0, and then at a higher frequency, the 0, 1 transition. Okay? And so if you see the transition from 0 to 2, you'd see a second peak. And so let's say we'd see that as well. Now the difference in frequency, if we multiply that by the Planck's constant, then we'll get the energy difference between V equals 0 in the excited state and V equals 1 in the excited state, or V equals 1 in the excited state and V equals 2 in the excited state. So the spacings of these peaks is equal to the vibrational frequency energies of the excited state, not the ground state. Okay, so that's the absorption of a photon, and these frequencies are usually in the visible light spectrum, or maybe even the ultraviolet, and so these are the transitions that you induce when you take the UV visible spectrum of a sample. Okay, so now what can actually happen when to the energy once you excite it? Well, the molecule won't stay in this excited state for an indefinite period of time. What will happen is that it will find itself in the lower excited state. So this usually does not occur by the emission of a photon. So, for example, if you get into the V equals 1 state, it'll, through collisions, transfer the vibrational energy and fall down to the V equals 0 state. And now you can emit a photon from the lowest vibration downwards. Okay? And notice that this energy difference is always smaller than this energy difference. Okay? So what you're going to see is a kind of a mirror image in the pink. So after I describe losing the energy and emitting a photon from 0 to 2, then I should actually draw a peak here, 2 to 0. All right. And if we emit this way, from 0 down to 1, that would be 0 to 1. And then finally, 0 to 0. And this is the only transition in the emission spectrum that has the same energy gap as 1 in the excitation spectrum. And it happens to be right on top of the other one. Okay, so it's a very typical pattern that you might see for absorption. That's these green lines, and then the emission spectrum. This process is called fluorescence. All right, so the fluorescence peaks are given in pink. And so you can identify the 0, 0 transition as it's the only frequency that appears in both spectra. And then from the 0, 0, you know the next one should be 0, 1 or 0 to 1 emission. And so you get a kind of a series of peaks. These spacings are the spacings of the vibrational ground states, energy levels. And these spacings are the the vibration frequencies of the excited state. Right? And so that's absorption and emission, and this is fluorescence. An example of fluorescence is they actually add something to laundry detergent that absorbs ultraviolet light, okay? And then the energy relaxes, and then it emits in the visible light. And so that's a brightener. So that's fluorescence that you might be familiar with. It's the reason why when you go into a theme park ride and they have these black lights, that all your white things glow, kind of this purplish white color. Okay, so the last thing we're going to do is talk about another process called phosphorescence. In phosphorescence, we're going to have an excited state that is spin forbidden. Okay, so for example, if these were singlets, the transition from a singlet to a singlet is allowed, but a transition from a singlet to a triplet is not allowed. So I just over for the purposes of keeping the diagram less cluttered. It could actually be closer in or even very close. But this would be an excited state triplet or something with a different spin symmetry. And so what will happen is in the vicinity of where these two curves cross, you can actually have the molecule convert from the singlet state to the triplet state without the absorption of a photon. So this process is called intersystem crossing. So this process of relaxation within the excited state is called internal conversion, where you convert vibrational energy to other modes of energy. But going from a singlet electronic state to a triplet is called intersystem crossing, because this is the singlet system, this is the triplet. All right, now once you cross over, okay, so then the energy might find itself down in the vehicle zero level for the triplet excited state. And then it gets stuck there because there's nowhere for this energy to go. You can't get any lower energy from vibration energy loss or rotation. The only way to lose energy is through the electronic transition to the ground state, but that is spin forbidden because you're trying to go from a triplet to a singlet. So this takes a long time. So phosphorescence can actually last quite a long time. So that's the type of process that goes on when you have like glow in the dark, these little greenish things that you can put in your room. When you turn the lights off, you can see them glowing for a long period of time. And the old TV sets, the cathode ray tubes, they would have phosphors in them that emitted light from when the electron beam hit them. You turn your TV off, you could still see the screen glowing. And that's because phosphorescence is a very long time. But eventually, you'll see the emission of the photon. Whoops, I guess she did a straight arrow. To maybe some vibrationally excited state. Okay. So that's phosphorescence and fluorescence.